Okay, so let's pick up our discussion with orbitals. Quick little review here. What we know about the atom is that the electrons can be in certain areas, but they can't be in between. It is a what we call quantized. So it's more like the electrons can be in a stair-step area, and it's not like a continuous spot all the way up, because we only see this wavelength of light, this wavelength of light, and this wavelength of light. We don't see anything that's in between those. So we call this quantized. So to then talk more about where electrons hang out, they hang out in orbitals, or this is where electrons are found. They come in various shapes. The first shape is simply a sphere. I'll put that in here like this so you can get a good look at it. The sphere is what we call the s orbital. And that's what the S stands for, is sphere. The other type of orbital is a p orbital. And the p in this case really stands for pi. I'm not sure why. But you see here that it's kind of like a dumbbell shape. And there's one that goes in the x direction, one that goes in the y direction, and one that goes in the z direction like this. So it's a three-dimensional thing. The last type of orbital is what we call a d orbital. And it's somewhat more complicated. It doesn't look like a dumbbell, it looks like a clover. And here we can see it going along the YZ plane. Here it's going along the Z and X plane. Here it's flat in the XY. Here it's aligned right on the axes, and here we got this kind of double pacifier looking thing. So they're very complex shapes. You don't really need to draw them, and I have some poor attempts at doing that, which I will show you. The letter, like I said, designates the shape of the orbital. The next number, the number that's in front of it, designates the size of the orbital. So here we've got a 1s orbital, here we've got a 2s orbital, which is going to be bigger. Here we've got a 2p orbital, and then a 3p orbital. It kind of extends itself a little bit beyond it. And that would be in all the various x, y, and z directions. And here we go to the d orbital, the clover leaf. We've got a 3 that's in close, and a 4 which extends to a higher energy level beyond that. So the big number gives the energy level. That would be this one here. The letter gives the shape. So P means a dumbbell, D means a clover leaf. And then there's one more number that indicates the number of electrons in each orbital. The maximum you can have in an s orbital is 2. The maximum you can have in a p orbital is 6. And the maximum you can have in a d orbital is 10. So let's look at how we build up the layers of the wave mechanical model. What we have is we have a small box that represents each orbital level. 1s followed by the 2s. The 2p is at a higher level, so that's written third. Then once we fill the 2p's, we can move then to the 3s, and then the 3p's, and then the 4s, and this is where it gets a little tricky. We go to the 3d. Now, if we were to write the orbital diagram for tin, we would lay out these boxes as we needed them. What we know about tin is that it has 50 electrons in it altogether. So we need to count them as we're filling in the boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And so we need to fill them in, one in each orbital. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, plus 10 up to 30. So this would be like 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, and 50. Now notice how we filled in the lowest levels first. That's the first rule. And then we only put one electron in each orbital until we had them all filled. Then we start doubling up. That would be our orbital diagram when we fill in the boxes. The electron configuration format is where we just write the numbers. So the electron configuration for tin would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and 5p2. So, if we can describe the locations of all the electrons. However, it gets kind of redundant, because once we get to this point, everything before it is really the same as the element before it. So what we often use is the noble gas configuration. And the noble gas configuration means we start with the nearest noble gas. Now, tin is going to be right here. And the nearest noble gas right here is krypton. So we know that krypton's configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Everything starts adding on then right here because we're adding 4s2, 3d10 to 5p2. So the noble gas configuration would be krypton, 5s2, 4d10, 5p2. So that would be the noble gas configuration. Let's go quickly go back over the rules here for filling in the boxes. The Aufbau principle means that we fill lowest energy level first. The Hund's rule says that we put one electron in each orbital. And then the Pauli exclusion principle says that in order to share, sharing requires opposite spin. So that's what the arrows indicate, that for two electrons to be in the same orbital, they've got to spin opposite ways. The reason these electrons kind of work the way they do is borne out in the layout of the periodic table. So the rows of the periodic table correspond to the energy levels. Note the 3 energy level starts here in this first D, where we have 4 S's here. And it tells you which order to fill them out in. The number of electrons that you add in the S region are here, the P regions are all over here, and the D regions are in the middle. So we can then determine the electron configuration of any element just by knowing where it is on the periodic table. So I hope that helped.